All right, let's take a look at question number 2 from the Modern Physics exam review. We have a non-relativistic electron, so easier, accelerated from rest through a potential difference. After acceleration, the electron has a deBroglie wavelength of 880 nanometers. What is the potential difference through which this electron was accelerated? So when I'm looking at this problem, the first thing I see, obviously, is the deBroglie wavelength here. And we have an equation that governs the wavelengths of particles. So let's just write that down so we can go ahead and work with it. We have our lambda deBroglie, or our deBroglie wavelength, is going to be equal to h divided by the momentum, h over p. Which is great. So now we have our wavelength, we have our h. Now we need to find p. Well, what is this? Where does the p come up? Well, we can equate p with our kinetic energy. So we can say that k is equal to, k is 1/2 mv squared. Sure, that's fine. But if we multiply this by m over m, k is also p squared divided by 2m, which is wonderful. Now we can convert kinetic energy directly to the deBroglie wavelength, which is what we're after. So now we need to find out what to do with this potential difference part here. Well, the momentum is going to come from the acceleration through the potential difference. And by that I mean the kinetic energy is going to come from that. So what we're going to do is equate this kinetic energy with the electronic charge accelerated through that potential difference. Now we have everything we need to solve this equation. The physics is done. Let's just do the algebra. So let's solve this p. So we'll say that p is going to be equal to 2meV, square root of that. So now we can take this and dump it into our deBroglie wavelength equation. And we'll say that lambda is going to be equal to h divided by this, which we have solved for p, 2me divided by the square root. So now we have the equation we need in order to solve. We have our lambda, we have our voltage. So what are we trying to do? We're trying to solve for this voltage, so let's do just that. The first thing I'm going to do is square both sides, so we'll get everything out of this root here. So we have our lambda squared is equal to h squared divided by 2meV. So now let's take the inverse, multiply both sides by h squared. So we are now going to take that 2meV is going to be equal to this, we can just say h over lambda squared. So now we're only one step away, one step of algebra, so let's divide everything by 2me. And now we're golden. So let's just take this down here and simplify into a single line. So we find that our delta V, the voltage required to get the kinetic energy required to get this wavelength, is now going to be equal to this quantity, which h over lambda squared, which is pretty darn small, divided by 2me. So we have our m, mass of the electron, is 9.1 times 10 to the negative 31 kilograms. Our electronic charge is, of course, 1.6 times 10 to the negative 19 coulombs. We have h, we have our lambda, and it's a little bit of a mess to plug it in our calculator, but once we solve, we find that our v is going to be equal to about 1.9 times 10 to the negative 6 volts. That is a very small voltage. So we can say it is about equal to 2 microvolts. And is that something that we might expect? Well, the wavelengths of electrons can be on the order of X-rays. So I would say for a small potential difference like this, having an electron with 880 nanometers seems pretty reasonable.